Welcome back to the course on the experimentation devel of a power system. In this class, we're going to see a few things. We're going to see how to assess the run of one AI agent powered by a large language model. So we're going to see how we can use AI to judge AI. While we do this, we're going to also explore a new source of uncertainty, or two actually. And this is bias and noise around the score. So we're going to see what happens where our judge is biased or is noisy. And we're going to see how this compound to the fact that the system can make mistake, and we can also make mistake in assessing the output of a system. So in a way, we can make a mistake in assessing our ground truth, let's say. So in lesson 1, we saw that eval is actually an experiment where we estimate the value of a random variable. We also saw our first source of uncertainty, which is sampling noise, and we made many assumptions. We dealt only with classification. Today, we're going to extend to general predictions. We assumed that there was no error in the labeling ground truth, and today we extend to noisy and biased ground truth. We also assumed that humans would label data at scale, and today we see how actually AI can help us get there. So the kind of classifier we used in lesson 1 were trained on dataset, which means we took a dataset, let's say a customer dataset, we train our classifier on the dataset, and then when we run predictions, we assume that we run predictions on similar data, right? So if you go to lesson 1 and pick your dataset and pick your classifier, you can then enter your sentence and have the model classify it. And what the model does, this is typical for the traditional, let's say, machine learning model, is you see here they write the probability of the sentence belonging to each class. So they give us a probability distribution basically of their let's say, belief. And if we then continue, and we can then see that in addition to that probability that we see here, which is really nice, we can also see the embedding. Because as part of this pipeline, there is often a part that actually embeds text into a hyperspace. We can actually see where our point is in the hyperspace, and we can get a sense whether our point is in an area where the model tends to be right or an area where the model tends to be wrong. Let's assume now that we want to use a large language model as a classifier. So we want to solve the same problem we had before, but without training a model on the dataset. We just use a large language model, let's say off the shelf, and we just use it to do our classification. So let's see how this works in practice. We go to our playground, we go to lesson 2, we click, and we go to the first tab where we see the example. And this is our LLM classifier. Basically, what we do here, we feed some example, and here we just put very few examples. In practice, you would put more, but we put example of sentences, and we say to which class they would belong, right? And basically, we count on the LLM based on these few examples to understand how the classification should be done. And what you see is that the machine learning classifier, in this case the LLM, can predict. You can, once again, as we did before, sample the data. You can spin the wheel to get your sample and see how well the LLM classifier is doing, and you can see examples that are classified correctly and example that the model classified wrongly. So in the playground, you don't actually have a connection with the LLM, so these are pre-computed sample that I've run here locally. What is interesting is that, just for machine learning classifier, we can use the same metrics. We have accuracy, we have precision, we have recall, and we have our confusion matrix. So more or less things are the same. There are a couple of important differences. We kind of have lost our probability, our belief that the item belongs to each of the classes. We might be able to get it back with a clever prompt, but it's a little bit more difficult with a pre-trained model. And also typically we lose the ability to see how the point embeds in a space. It's possible, especially if you have access to the complete model, but it's a bit more challenging to get the same output. So we can get the accuracy, we can get precision, we can get recall, we can get confusion metrics. It's a little bit more difficult to get probabilities that each sentence belong to a given class, as we had before. So we lost two things here. We lost the ability to have the embeddings in a space, and we lost the ability to have confidence of each sentence belonging to each specific class. The reason why I love models that actually emit confidence and belief in an item being part of a certain class is because we can actually assess the calibration of the model. So we can take, for example, the sentences for which our model has a belief of 80% of the sentence belonging to a class. And a well-calibrated model, in that case, should be right 80% of the time. If it's correct less than 80% of the time, our model is overconfident. And if our model is instead correct more than 80% of the time, then our model is underconfident. And you want a well-calibrated model, just like you want a friend that when they're sure about the answer they're going to give you, they actually tell you that they're confident. But when they are not sure of their answer, they actually tell you, I don't know, I'm not so sure, maybe better check in some other ways, right? So I kind of love this ability of the traditional model to tell us the confidence, because we can easily assess the calibration of the model. And a well-calibrated model is a treasure to actually cherish, because once the model is well-calibrated, you kind of know. If it tells you, I'm sure, the answer is going to be that one. And you know that if the model is really not sure, it's going to let you know. So you can take some action, for example, ask a human to classify the sentence for you for that case. So one other interesting little tricky part with using LLM for example, classification of prediction in general is that they may a little bit go off script with the answer. So maybe with the traditional classifier, the model is hard-coded to provide you a probability for each class. So that's the only possible answer. With the LLM, you get text back, and you hope that the text back is a class. Sometimes the model puts some choreography onto it and doesn't answer just the class. So the comparison of what the model is answering you and the matching with the class sometimes is not completely trivial. This problem is kind of disappearing as new models are very good in following instructions. And so if you tell them, give me back one of these classes, that's the answer they're going to give. But it's something that we must be aware and we must remember to check. The nice part with GenAI is that we can actually tackle more complex use cases, more complex than quote-unquote just classification. So for example, here you see a GenAI system that takes a court case transcript and create a summary of this court case. And this creates, of course, many interesting possibilities that we want to capture. It also creates some challenges from the perspective of the assessment of the system. So, for example, it's really hard to assess if this matches a ground truth, even if we had it, right? It could even be subjective. It's really hard to get ground truth. You would have to go through court cases and summarize them, unless you have some other way to get this quote-unquote ground truth. You have multiple dimensions against which you may want to score this. So you may want to focus on whether, for example, it's accurate, whether it's complete, meaning it, let's say, includes all relevant aspects that you care about. You may want to check whether the text is fluent and well written, and so on. And you may want to score these metrics over a certain scale, let's say typically a 1 to 5 scale. And the common way in which you assess this is, so you either by hand create the ground truth, then quote unquote by hand you run the GenAI over the court cases, and then you as a human assess whether the answer is accurate, complete, fluent, and whatever metrics you want to score. Or you use an LLM judge. So whatever criteria you have, you give them to a judge, and then you give to a judge the ground truth answer and the GenAI answer, and you ask the judge to judge the answer. Or you could even do it without any ground truth. You can just give to the judge the input and the output of the AI power system and say, hey, I have the system, I gave it this input, the system produced this output. Can you score whether the output makes sense for the input? And let's see how this works in practice. So here is how it works in practice. We go to the playground at the usual URL, and you select the lesson 2 playground, and you see this tab about the scorecard judge. And that's what we were just talking about. So here we define some metrics, and here they are briefly specified. For a use case, you may want to be more specific about what each of these metrics actually mean. And there is also the overall metric that you see here. And the overall metric is not judged, it's simply a formula that is computed based on the other scores. So these are the two prompts that we have. We have the prompt for the GenAI system that actually creates the summary. And then at the bottom, there is the system that receives the actual court case, receives the summary, and then judges the summary. And here it's a very simple judge. We pass the metrics very simply defined, and we ask to give us a JSON object with a 1 to 5 score as a result. So that's what we do. And we can also, in the playground, we can see examples. So you see here, there is a link to the actual court case. On the left, you see the summary, and on the right, you see the judgment, let's say, on the summary. You can click on this random button to see other examples, or if you want, you can just click on Jump to a Low Scorer, and you will jump to some court case where the summary has received a low score by the judge. So that's what you can do in the playground. And you also can see at the bottom here, there is a comment where the LLM can say why, the LLM judge can say why the score is low. As usual, we typically score a sample. So we have a certain number of, let's say, example, and let's assume they've been manually judged, or let's assume that we run a TLM judge over specified numbers of court case, and then we assess whether our system is doing a good job according to the judge. And once again, as we change the sample, you see that we have our little sampling noise. As we change the sample we are looking at, our perception of the accuracy of the system may change. And you can spin the sample and try with different samples, and you're going to find some examples for which the accuracy on the sample is very close to the true accuracy that you're likely to experience in production. But we have just a sample, so we don't really know. Or in some cases, your sample will be closer to production, and you don't really know unless you sample more points. That's exactly the sampling noise we have seen in the previous lesson. It applies also here. There is one thing that I would like to notice. Well, actually, there are many things, but let's start with one here. Because we have multiple metrics that we are judging, it is more likely that as we get a sample of points and as we run the eval on the sample of points, it is more likely that at least one of these measurements that we take is going to be far away from the real mean. Right? So the more are the things we measure, the more likely then in our sample, just by chance, due to sampling noise, at least one of this measure will be off its true value. Right? So the more things we measure, the more likely it is that at least one of them is far away from the true value. There is a little aspect I want to mention that is, I think, super important. It has nothing to do with uncertainty or noise, but it changes completely how we view the results of an experiment. So, for example, you see here and in the playground, we saw that the overall metric is some computation over the other metrics. So what you see here is that, for example, the overall metric is a weighted average of, is a linear combination of the other three scores. And this gives 45% of the weight to the accuracy and 45% to completeness, and then it gives 10% to fluency. So it creates a combination of these three scores to compute the outcome. And this is completely arbitrary, or at least in what I've done here, it's completely arbitrary. You could claim that, I don't know, accuracy for you is more important, or fluency for you is really important, and you may want to change your weights. As you change these weights, the outcome, the actual number that you get, changes completely. And the reason why I want to flag it is because sometimes this choice is hidden somewhere in the system. Maybe it's not really thoroughly discussed, but it changes completely how you look at the results. Let me give you one very concrete example so you can know exactly what I'm talking about. Very often people like to see these scores or these metrics on a 0 to 1 scale or a 0 to 100 scale rather than 1 to 5. So very often we ask the RLM judge for a qualitative score, very good, good, bad, very bad, that kind of maps to a 1 to 5. But then when we report results, sometimes people are more comfortable in providing a 0 to 1 or a 0 to 100 scale. And so if you want to do this, you need to map your qualitative score or your 1 to 5 score from the RLM judge into a 0 to 1, right? And you may choose a different reasonable way to do this mapping. So in this case, you see, for example, a linear combination. So if your score is 1, you get a final 0 to 1 mapped score of 0. If you get a 2, this maps to 0.25. If you get a 3, we map it to 0.5. And if you get a 5, we map it to a 1 or to 100. And you can do this. And the point I want to make here is that you have multiple very reasonable choices that you can make to do this mapping, right? So for example, you can say in this case, the example, I'm just taking 1 to 3 to keep things simple. So I assume my judge returns score in a 1 to 3 scale, and I need to map it to a 0 100 scale because I want to report results on a 0 to 100 scale, right? And so in the first row here, with the first approach, I'm mapping a and the RLM score of 1, I'm mapping to a 0. If it gives me a 2, I map it to a 50. If I get a 3, a top score, I map it to 100, right? And that's a reasonable way. Or you can say, no, I really want to be, top heavy. If it's 3, I reward with a 100. If you give me a 2, I'm not going to map it to a 50. I'm going to map it to a 30, right? Because I really want to reward excellence. Or you may do the opposite. If you say, okay, if it's 2 or 3, I'm happy. So I'm going to map it to a 70 and a 3 to 100, right? And so you have basically a bunch of different choices, and all defensible, all reasonable. And the point I want to make is that the choice you make in having this kind of mapping makes a big difference. Not only makes a big difference in the absolute 0 to 100 value that you get, of course, if you do a different mapping, you're going to get a different number. But it's also going to be directionally different. And what I mean with this is that you may have 2 systems, like one that produces the score in row 2, and the second system that produces the score in row 3. And you can map this differently. And based on how you map them, you may decide that one is better than the other. And these are on a, scores are on a 1 to 5 basis in the slide. But the point is, the way you choose to map the score to a 0-100 space is going to make a difference. Also in you believing that one system is better than the other. I make this point again, nothing to do with sampling noise, but it's a decision that very often gets maybe swept under the carpet or taken lightly, or maybe not even communicated, or maybe you take defaults that are in the system. And the point I want to make here is that this is a very consequential decision, so you need to make this intentionally. You need to be aware of what you're doing, of what matters for your use case, and take this into consideration when you map your score to a 0 to 100 scale. So I promised you we will see today one more form of uncertainty or noise. And I'm just putting here a book I really love, Noise, written by Kahneman, Sibony, and Sunstein. And it makes a lot of interesting points about noise and bias in judgments, and about how organizations are kind of insensitive or blind to noise. So I suggest you to read it. It's a great read. So the point I want to make here is we have seen our GenAI system. It's summarizing a lawsuit or court cases. And so we have the system, and then we have the judge. The judge is the output of the system. So what's very interesting here is that our system can be noisy or biased. So for example, it can consistently forget a certain part of the court case, or it can be noisy in how complete it is. And also the judge could be noisy or biased. So there can be some randomness, some random fluctuation in the ability of the judge to be a good judge for certain court cases. Or maybe there could be a consistent bias. The judge maybe can consistently overestimate completeness or underestimate completeness. And the way we use these terms, noise and bias, noise is generally some random, inconsistent, let's say, random error that we find in the system or in the judge. And bias is a systematic error, a systematic deviation in one specific direction. So overestimating or, for example, underestimating completeness. So if we go to our playground, and again, we click on lesson 2 and specifically on the tab about the uncertainty compounds, What we see here at the start is if you select this dial here, for example, to 40, what you see here is what we saw in lesson 1. So basically, the error in our estimation of the true mean, which we can only estimate through our sample, so our sample mean. And we can see that here, you can see that on this second chart on the right, this is the error of each judge. So this reports the error that is each judgment is making. And as you can see, the error is 0. So the judge doesn't make any error in this setting. The reason why we get a sample mean which is different than the true mean, it's just because the specific sample we chose, we were a little bit unlucky, and the quality of our system was on average 3.48, while the hidden true mean, which we don't know because we don't have access to the entire population, is 3.8. So we got a bit unlucky with our 40 sample, and that's our sample mean. If you click here on the redraw and rejudge, you can redraw a sample and you're gonna get a different mean. You then can click here when we have linear at 0, 100 and squared 0 to 100. That's basically transporting the view from the 1 to 5 scores to the 0 to 100 score. So you can see that, for example, in the 0 to 100 scale with squared mapping between 1 to 5 and 0 to 100, we have a measured mean of 48 out of 56, so a gap of 8 points in this case. So that is in case our judge is perfect. So we are in lesson 1 world, perfect judge, and all the error we get here is our sample mean. So now let's add some lesson 2 content, judge bias and judge noise. So we go to the noise dial and we bump it up a little bit, and then we see that in this tile of this chart, tile number 2 here, we see that the judge is not perfect anymore. Sometimes it's let's say overly positive, and sometimes overly negative, and that's because we added some random noise. So we assume that the judge is going to make sometimes some random errors, and sometimes be overly positive, and sometimes be overly negative, and sometimes it's just right. So it's a random noise with a mean of 0. We can also assume that our judge is biased, and here what we mean is, in this case, we are sliding to the left, so we're assuming the bias, the judge is going to be on average overly negative, so it's a bit of a severe judge. And when we do this, we can notice that the measure mean quality from the sample is around 3, while the true mean is 3.80. So that's a massive difference. It's 0.8 on a 1 to 5 scale. So it's really a high difference. And part of it is due to the sample. We were a bit unlucky with the sample to start with. The system was not doing very well. But in addition to the system not doing very well, now the judge on the system is also overly negative, right? And there is also some noise that adds to the confusion, right? But the contribution of all these factors means that now we have a quality of a measure quality from this draw that is very, very different from the real mean. One question I often get is whether noise cancels out. So the goal we have here, let's assume that our goal is to understand what is the mean quality of our system, right? So what's the, let's say, the average accuracy of our system. And the question is, if the judge is noisy, not the system, but the judge, if the judge is noisy, is this a problem? Because noise is random, so sometimes we're gonna make a mistake in the positive side, sometimes in the negative. On average, do they cancel out? And as you can imagine, the answer is not really. So what you see here is if you go to the Bootstrap section, what you see here is a system where we have zero judge noise, zero judge bias, and we have a sample of, in this case, 43 items. And we have the true mean is always 380, and we have the measured mean of 3.72. And the difference here is only due to the sample. We have been a little bit unlucky again with the sample, but not too much. Now, what happens if we increase noise? So this histogram below kind of plots our, let's say, our belief on what the true accuracy is given the sample of 43 items that we have seen. We're going to see later how to compute this, this belief. It's a very neat trick that is much more satisfying than just getting a mean. But let's park it for now. What I want to show is that if we bump up the noise, then what happens is the spread of our belief gets larger, right? So on our sample, we may be unlucky due to the sample that we had, but also because of the noisiness in the judge. As we draw different samples, the width, so the extent of our uncertainty, is going to be higher. So if we have a noisy judge, the judgment will be a little bit all over the place, and therefore this kind of reduces our certainty about what the true mean is actually going to be. So if you click redraw and rejudge many times, you can see that the scores are swinging way more than when you set the noise to 0. When you set the noise to 0, the score swing less. When you bump the noise up, you can see that the score swing by a higher margin from draw to draw. Right? So if all we have is our 43 points, we don't have the luxury of having judgment on a lot of points, then the judge noise does hurt us, right? If we have a lot of points, then things change, and our estimate of the mean is going to be closer to the true mean. And of course, then if we get the noise to 0, it's going to be even better. One final point I wanted to make from the playground, from this section, is this one. If we go to this section on the judges and bias and noise, what we can see is that as we dial, for example, the bias, let's say we have a negative bias, right? What you see in this chart here is that, so the bar on the left is the error in judgment we make per example, and this blue, violet, whatever bar is the error we make in estimating the mean quality of the system. So that's really the parameter we are trying to estimate. And as we dial the bias, they both grow in the same way. So here we make an, let's say, error of 0.5 on average. We are being more restrictive, so we assess things more negatively, and both the error on each individual example is going to be around 0.5. And also our estimate of the mean quality is going to be off by 0.5, right? Now, what happens when instead we increase the noise of the judge? So we have a noisy judge, And what we see here is that as we increase the noise, our mean error, meaning our estimate about what the quality of the system on average is going to be, is affected by noise only in the sense that it makes this estimate more uncertain, but it doesn't push it in any specific direction. Because noise, we assume, is random. Sometimes we overassess, sometimes we overassess, we underassess. Okay, so this is why the blue bar doesn't grow as we grow the noise. But the red bar, the individual error that we make, that one keeps growing if we increase the noise. It doesn't cancel out. So the error on each individual example is the sum of the bias error and the noise error, and those two do not cancel out on average. They compound, and we're going to see how they compound. So I think this is an important point. If you are like a citizen being judged by an AI judge, it may be that, the judge is noisy, and you say, okay, on average, people sentenced for crime X should get 10 years, and that's consistent with what we observe. But if the judge is noisy, then you have a bunch of people getting 15 years and a bunch of people getting 5 years. And so we are being wrong on both counts as a judge, even if on average our estimation about the average judgment is actually correct. So this is just to emphasize the difference. Noise kind of cancel out if we're trying to estimate the mean. What happens is that noise just increases the uncertainty. So if we keep redrawing sample and sample and sample, we see that if the noise is higher, our estimate of the mean is going to be wobbly, but it's not going to be wobbly in any specific direction. While if we reduce the noise, then our estimate of our mean error of the judge is going to be less wobbly. And in fact, with zero noise, our estimate is just going to be dependent on, the sample that we get. So for those of you who love statistics, the error, as we said, is the combination of bias plus the noise. And often when we measure error, we measure the square error or the root, the square root of the squared error. And this is if the error is bias plus noise. Noise can be positive or negative. When we compute the square error, and specifically the expected value of the square error, then we can see that the expected value of the square error is the square of the bias plus the square of the noise. And again, you can skip this slide and these concepts if you're not into statistics. We're going to see this more in a deep down. But I think the message here that I think I want to make is organizations tend to be blind to noise. They tend to fight bias aggressively and be very resistant to bias and dislike bias, but somehow be more tolerant to noise. And I think the point I want to make in this slide is that bias and noise equally hurt an individual judgment. Right? Noise may kind of cancel out if all we are trying to do is to estimate the mean, let's say, accuracy of the judge. But if what we are trying to estimate is the error in judgment that we make each time, then this error compound with bias and noise. So that's pretty much all I wanted to say for now. There are many kind of ways why the LLM judges are biased. I'm going to provide example in the playground rather than listing them here. There are many ways in which the way we craft the prompt may lead to a biased judge. Right? And you can measure the bias in many ways. And again, we're going to see some examples in the playground. So what you can do besides trying to reduce the noise and the bias is measure it. So you go through a process called calibration, You run the LLM judge, you compare it with human judgment. And humans can be noisy too, because the problem can be truly subjective, right? And what you measure here is, you can do it in many ways, but essentially you measure the disagreement between judges and humans. And so you kind of get a sense for how noisy the judge is. Let's assume that the judge is not biased. If it's biased, we can consider that too. But we can also see the noise that the LLM judge has with compared to the ground truth, let's say, which is what the human would provide. And once you have this noise measured, then you can consider it when you report your estimate. The higher is the noise, the higher is the uncertainty you're going to want to report when you tell the results about the experiments that you've run. Right? And once again, we conclude the lesson by taking a look at how we can easily report about the uncertainty. If you go on the lecture page, you see this Judge Playbook tab. If you go towards the bottom, you're going to see a link to the Bootstrap calculator, and you click on that link. And that's really a calculator where, in first approximation, you don't really need to know much about the theory behind it. You put the results of your judge. In this case, they are in scale 0 to 100. It will be the same for a scale 1 to 5. And then you click on the little compute button. And this interface essentially will tell you what to report. So for example, with the number written there, here we see what we can report about the 95% credibility interval. So here, for example, we are pretty sure that the true mean is between 88 and 90. So it's a fairly small range. And here we have the probability that our belief that the true mean is, is greater than 80, greater than 90, greater than 95, right? So here we are pretty sure that it's greater than 80, very doubtful it's greater than 90. If you have a different data set, you can actually go and, you can make changes. For example, here, let's assume we have some, some very low scores, and we add them to the mix. And then we click the compute button once again. And what we have seen is, because we have put some very low score, now our little calculator is a bit less confident. So now it's telling us, I believe your true quality is between 80 and 89, essentially between 80 and 90. And right now I am very doubtful that the true score is greater than 90. This little histogram you see here is essentially the belief that the true mean sits in at a given value, right? And this is done through Bootstrap. Bootstrap really works well if you have like greater than 100 data points. It's a bit shaky below 100, but it's a great technique. So if you want to know more about what is behind this little calculator, join the deep dive, and we're gonna talk about Bootstrap in our deep dive. So in summary, we have seen that our reported score is a joint property of the system and also of the judge. We have seen that bias and noise in the judge can add to sample noise, so they compound. We've also seen that there are different issues with different kind of fixes, right? So you reduce bias by working on your judge prompt. For noise, you can also work on the judge prompt to make it a little bit more robust, but be mindful that there is a degree of subjectivity that you may not be able to reduce. And finally, we have shown the Bootstrap calculator as a way to report properly on experiments that are affected by judge bias, judge noise, and sample noise. The Bootstrap is a general calculator. You can always use it once you have let's say 100 sample or more. And with this, thank you for joining this lesson, and we're gonna see you in the next lesson.